Retrieval Augmented Generation is a powerful framework that combines information retrieval with generative AI. In this process, we begin with the vector database retrieving relevant content. This content is then combined with a system prompt and passed to the language model, or LLM, for advanced processing. The LLM generates a personalized response based on the provided context, which is finally delivered to the user, ensuring a customized and enriched experience. In this diagram, we begin with the vector database retrieving relevant data. This data is combined with a system prompt and passed to the LLM for processing. The LLM generates a contextual response, which is finally delivered to the user, creating a personalized experience. In this diagram, I am explaining an enterprise solution leveraging generative AI to create customized content-based experiences. At the core, we have an AI processing node, represented by the LLM, or large language model. This LLM is the intelligent system responsible for processing diverse content and generating personalized responses. Consider different sources of data that feed into this LLM. PDF documents are one of these sources. The AI can extract relevant information from PDFs, such as policies, reports, or product details. Next, we have the CRM system, which provides customer-related data. This information allows the LLM to generate responses that are tailored specifically to individual customers, improving personalization. We also have a database node, which supplies structured enterprise data. This might include product inventories, financial data, or any proprietary information required to answer specific queries. With all these inputs, PDFs, CRM data, and structured databases, the LLM is equipped to rich, context-aware responses. The next step is the generated response node. This is where the AI compiles the data it has received, analyzes it, and creates an intelligent response tailored to the user's query or requirement. Finally, this response reaches the user. The user receives an enriched, informative response that brings together the power of enterprise data and generative AI. This use case showcases how generative AI can enhance enterprise capabilities by leveraging multiple sources of proprietary content to deliver personalized and insightful user experiences. We're exploring the difference between traditional search engines and large language models, also known as LLMs. On the left, we have the traditional search engine, like Google. Traditional search engines are designed to help users find information by providing links to relevant content across the web. They use indexing, ranking, and search algorithms to direct users to websites, where they can explore and gather information for themselves. Now, on the right, we see a large language model, such as OpenAI's model. Unlike traditional search engines, LLMs go beyond simply offering links. They can synthesize information from multiple sources and generate meaningful responses directly. This means that instead of pointing you to a web page, the LLM can provide a coherent, human-like answer, pulling from its training data, to give you the insights you need without extra searching. Consider a real-life example. If you use a search engine to ask a question, you would get links to articles, blog posts, or videos. You would need to open those links, read through the content, and find the answer yourself. In contrast, with an LLM, you can ask the same question, and the AI will generate a detailed, specific answer, directly responding to your query. It uses advanced natural language understanding and generation to summarize and synthesize information from all the content it's trained on. This approach not only saves time, but also makes complex information more accessible and easier for users to understand. So in summary, while traditional search engines are great for finding resources and diving into information, large language models aim to provide ready-made answers that are context-aware and more conversational. Let's understand the RAG flow here. Let's start with the input question. This is the user's initial query, the question or prompt they want the AI agent to answer. Next, we move on to prompt engineering. Prompt engineering includes crafting detailed instructions and selecting relevant content chunks, that can help the AI generate an accurate and meaningful response. It's a crucial step that ensures the LLM understands the context and intent behind the user's query. After prompt engineering, the workflow reaches the LLM processing stage. Here, the large language model uses its understanding of the prompt, combined with training data, to interpret and synthesize the information into a coherent answer. Finally, we have the response generation step. At this stage, the LLM generates a well-formulated response, which is sent back to the user to answer their original question. In summary, the RAG workflow starts with an input question, applies prompt engineering to prepare the content, processes it through the LLM, and ends with the generation of a meaningful response. The basic Retrieval Augmented Generation, or RAG design pattern, is a powerful approach that combines retrieval and generation. It leverages large language models, also known as LLMs, to produce more relevant and accurate answers. Let's break this down step by step. The process begins with retrieval. The retriever fetches information from external or private content. This can include proprietary documents, databases, or any context-specific information. This step ensures that the LLM has access to the most relevant context, instead of relying solely on its pre-trained knowledge. Once the relevant context is retrieved, it's passed on to the large language model. The LLM then uses this context to generate a response, one that is coherent and enriched by the specific information it just received. Finally, we get a generated response that is tailored to the question or need at hand. By combining retrieval with generation, the RAG pattern allows the LLM to generate answers based on external, proprietary, or private content, not just what it learned during training. This makes RAG especially powerful in enterprise scenarios, where the information used to generate responses needs to be fresh, context-specific, and even private. The combination of retrieval and generation offers a unique advantage in providing customized and context-aware answers instead of merely pulling from pre-existing knowledge. In this segment, I'm going to break a little more on Retrieval Augmented Generation pipeline for you. The process begins with the user query. Next, the query undergoes vectorization. This step transforms the user's query into a vector, allowing us to use mathematical operations for further processing. After vectorizing the query, we proceed to content retrieval. In this step, the content is broken down into chunks. Each chunk is vectorized individually to facilitate comparison with the query vector. We then match the query vector with the content vectors to find the most relevant chunks. Once we have the top content chunks, we move on to prompt construction. Here, the retrieved chunks are combined with instructions and the original user query. The generative model, often referred to as the LLM, processes this prompt. The LLM synthesizes all the information and generates a meaningful response. Finally, we reach the response output, which is delivered to the user. This flow illustrates how each technical step works in sequence to transform a simple user query into a rich, informed response, using the power of retrieval and generative AI. This is the end of pipeline and response to the user query shown as response to user. Until now, you mostly understood the pipeline. In this segment, let me explain the key components in Retrieval Augmented Generation, also known as RAG. The first key component is the vector database. This database is responsible for storing vectorized content and supports similarity searches to quickly find relevant information. Examples of vector databases include Pinecone, Milvus, Weaviate, and FAS. Next, we have the embedding model. The embedding model's role is to convert text, whether it's a query or content, into vector representations. These vector representations help the system understand and relate different pieces of information. Examples of embedding models include OpenAI and sentence transformers. Moving on, we have the large language model, or LLM. The LLM is responsible for generating natural language responses. It uses the embedded information to craft a coherent and meaningful response that can be easily understood by the end user. Examples of LLMs include GPT-3, GPT-4, Claude, and Llama. Finally, we have the application interface. This is the user-facing part of the system, typically a chatbot or an API that allows users to interact with the RAG system. It provides a simple interface where users can ask questions and receive insightful responses generated by the LLM. These components work together to make Retrieval Augmented Generation effective, enabling applications to pull relevant content from a vector database, process it using an embedding model, and generate meaningful responses with a large language model, all while keeping the interaction smooth through an easy-to-use application interface. Thank you for listening, and I hope you now have a better understanding of the key components of RAG. In the next video, I will go to the code and explain how to use these components in Python. See you in the next video. Thank you for watching. If you found value in this video, I'd greatly appreciate it if you could take a moment to subscribe to the channel and click the bell icon. This ensures you don't miss out on future content designed to help you grow and achieve your goals. Your support means a lot and helps us continue sharing insights and ideas. Thank you, and I'll see you in the next video.